but it should be a fun lecture. Yeah, and just, yeah, good. All right, so those are the administrative issues. And the week after that, we'll talk about that. That will be guest lectures too. That should be fun. Okay, any questions about the admin stuff?
Picking the presentation paper.
Okay. How did it work?
Yeah.
Well, we should pair up.
No, but like
That was the
where
first
do we-
problem.
Where shall we post our choices or something?
Yeah, I guess maybe the easiest would be to just like create the Google Docs and then copy all the papers there, and then you can just like tag it that like, oh, I chose this. And for these presentations, after you choose it, yeah, like message me so that we can discuss in what order and when, and so that it makes sense. And whether the paper even makes sense. Because I have posted a bunch of papers, some of them I only glossed over, maybe many of them. They did make sense, but I will take a more thorough look before we're gonna commit to a paper. And this should happen as we go. All those papers are kind of, yeah, I think that they are pretty good. It's a mix, the papers that I posted on the website is a mix of empirical and theoretical papers. For this class, I expect people to be more inclined to choose theory papers. Empirical papers, though, are quite important in many ways because they create, some basic understanding of what's happening in the space. But presenting an empirical paper is maybe, not really for this class. It could be like 5 minutes, like these guys have these empirical results, these are the curves, this is how it looks like, and this is how it relates to theory. But, like maybe spending, I don't know, an hour and a half on detailing some experiment that it does, I don't know. This class is not ready for it. So when you're choosing the papers, keep this in mind. Okay, any other questions? Yeah.
The link you select doesn't work.
Yeah, I told you.
Wait, you told me?
You have to solve a puzzle. Kind of like.
No, it doesn't exist.
Yeah, exactly. That's the
Oh,
puzzle.
I see.
That's, oops. Yeah. Like if you look at the URL, you will see. It's one step deeper thinking is required, reasoning in LLMs and beyond. It will work. I think. Did? Yeah. Okay. All right. Okay. Good. Anything else? Okay. So then let's start. The last time we talked about this somewhat abstract formulation of LLMs. So I just want to start with that to recap of what's happening. So we're talking about that we have an alphabet, and we are going to have strings formed out of the elements of the alphabet and functions processing these strings. And we're going to have this family of functions, which are the transformer functions, which are parameterized by some basic spaces, M, Q, K, V. There's a workspace. So in addition to the alphabet, we have the workspace. And the last time I was mainly focusing on the workspace is RD, but you can imagine that it's a structure space like strings themselves, or like some data structures. Like you could be more abstract with the workspace. And That's why one of the reasons that, because we're gonna talk about this language RASP, and there, this workspace is not really hard. But the picture that we're gonna have about transformers is still going to fit that. So these are functions from workspace to workspace, and there is a function U, that's the embedding function, or that's an unembedding function. The embedding function is E. E is going to map sigma to the workspace, and U is mapping the workspace to sigma. And for every n, so we're fixing an n, we define this f. Well, we define, okay, so we define f as a map from every finite string to every finite string, maybe, well, I could have written just sigma star to sigma star. Okay? And if you fix an n, and you fix this, like you talk about how f behaves on strings of length n, okay, maybe empty string, I don't know. Don't bother too much with that. It's not doing anything. Then you have the component-wise application. Okay, maybe it's better to write here. The embedding function is applied component-wise for every element of the string. So you can imagine that string comes in, it has these letters, A1, AN. So function U is applied at every position. So U of A1 is the first output, second position, U of A2 is the output, last position, U of AN is the output. So U transform, this was not U, this was E. With the embedding function, elements of sigma n are transformed to elements of wn. So this is a component. So this just denotes that this function is applied component-wise. And then a bunch of transformer layers are applied. Finitely many of them, capital L. Each of them are going to look the same, and I will write on the definition n. And after that, so these are functions that map strings of length n over a workspace to strings of length n. Yeah?
I just had a question about the unembedding function. So now we consider that the transformer produces characters instead of a distribution over characters.
Yeah. And then later on we will just
Okay.
extend the definition so that it produces distributions. Yeah. Okay. Because it is just simpler to talk about this first. And it kind of gives you the picture anyways. The only change that is going to be required is to this unembedding, where it's going to map, like instead of maps to alphabet, it maps to distribution over alphabet symbols. And it's doing that position by position, so it's component-wise. It's kind of the same thing. But we can talk about how that is happening. So there are these L transformer layers, and that's where the magic happens. So these transformer layers take workspace string of length n, return such a string, and they take the form of the composition of an MLP. Oh, that's applied again component-wise, but first the attention layer computation happens. And so this ML function is an element of M, and AL of n maps again workspace elements to workspace strings to workspace strings, and ALM x I. So the i's output is just the i's input plus summing over positions from 1 to n, sometimes 1 to I, minus 1, of the result of the following computation. For every position I, you calculate some value on that position. This is the output of QL, and you also calculate for every position this query value and key value, and you take all pairs and then you calculate like how aligned they are with this function A, which is an element of A, is an element of Q, is an element of K, and this gives you, well, in the simplest setting, binary value. This tells you whether you're attending when you're trying to calculate what should go into position I, whether you're attending to position J, then you get a 1, and if you're attending to that position J, then you collect the information that position. So this is V of xj. So in actual transformers, all of these are linear neural networks, or ReLU neural networks, really simple, one layer stuff, nothing complicated. And slight difference to what is here is that, okay, sometimes you are normalizing this. So J goes from 1 to n, and sometimes I minus 1, and then you have this law. But you also calculate the grand total of all these attention values, which means that if you look at these coefficients, they sum to 1. Yeah.
What's this n/I minus 1?
Yeah, it's just my imperfect way of signaling that sometimes the upper index is I minus 1, sometimes it's n. Okay, I should just catch it off it. These are bells and whistles. So one bells and whistle is going to be, I don't have a different color, where you're replacing this n by I minus 1. That's a sort of masked attention or causal attention. When you're at position I, you look at all the previous positions and you're collecting information from there. So that's a special case of masked attention. So this attention calculation is a little bit, looks like complicated, but you should think about that. So this whole transformer business is, except for this attending other positions, occasionally you're caring about what information you're carrying at the given position, and you just try to kind of enrich that information until you get to the end, where you are going to maybe project the information that you collected to something meaningful. So this, let's add things together, kind of represent, you can imagine that that just grows a tuple, like it's just expanding things. It's never erasing anything. Whether that actually happens in a transformer that uses these RD vectors or not, like, no one really knows, but that's kind of the intuitive thinking of what's going on inside an attention. And then here you can think about, okay, like I keep what I already know at that position, like that's the relevant information I'm currently carrying, like you're somewhere here in the middle, you calculated something, and then you look at maybe the previous positions, all of the other positions, and then you're looking for, like, can I collect useful information from my neighbors left and right? So you're kind of propagating information. If the upper index is I-1, as usually is done these days, then that means that you're only looking at preceding positions. You cannot look forward. So you look at preceding positions and you're asking questions. Oh, can someone tell me whether on the previous position, I don't know, ball was mentioned, or I don't know, something about the sky was mentioned, or whatever, right? So that's your query. And then at that specific attention layer, you would have formed some query. And the key computation is happening for every of the positions. And the keys are just like, oh, the key is just preparing for, if the question was such and such, I would be there to react to that. So that's the key. And the value computation is also happening at every of the positions. So you can imagine that instead of this embedding, like every attention layer after that, there's three things computed. The keys, the queries, the keys, and the values. And then they are combined in this form. And this is order n computation, right? Like for every position you do order n computation, so it's gonna be n squared. It's a matrix. It's a matrix vector product, right? So you do all of this, and then you're collecting the relevant information and you just keep it. And after you did that, there is also something that's happening after. This is usually how people do things. Sometimes there are a bunch of just these attention layers next to each other. So this is also best and Vissos. And then there comes some MLP layers. But this is a very common way of arranging things. And people say things, oh, MLP is like stores knowledge, and like this is kind of syntax, grammar, kind of, spreading information. Yes?
So why aren't the embedded and unembedded maps inverses of each other?
Why are they, or why aren't they not?
Why aren't they not? Like
Sometimes they are.
Okay.
I mean, like they're not really, because different spaces, right? But it's like one of them. So if you're concatenating, like you do first embedding and then you do unembedding, oftentimes things are set up by default in such a way that you get back the same thing.
Okay.
Kind of requires the embedding to be bijection, which might not be true, right? If you want to invert it.
The embedding is definitely not a bijection, because like in the actual architectures, because this is finite and this is infinite.
So you cannot invert it, right?
The embedding cannot be inverted, but if you first apply the embedding, you just get very special vectors. And for those vectors, the unembedding can invert things and you can get back the same. But there is no guarantee that, well, I mean, like, you will move away from those vectors maybe, and like, who knows what happens in the vicinity of those. The unembedding, you should imagine that, well, this is for every element of the symbol is just a vector, and then sometimes you just use the same vector, and then the way you compute the unembedding is that you compute inner products between the vectors, and then the largest inner product wins. So that's the argmax way of doing the decoding. So maybe at this point we can talk about the probabilistic way of decoding, which would be very similar. So that unembedding, and then I come back to that. That unembedding would, so W is RD, and then U of X is a probability distribution, and each component of the probability distribution is associated with a vector of the alphabet. The dimensionality of this is n, capital N, which is the number of symbols in the alphabet. So each element of the alphabet is maybe through the embedding vectors, okay, but potentially is associated with some vector. Let me call these vectors W1 to W2 to Wn. And then what you do is that you take inner product of W, okay, the i's position, so I don't have to write a lot, takes the inner product with X and divides with the sum of all of these, capital N. So softmax transform. Right? So that just creates this probability distribution. And so now you have this soft unembedding. So what do you do with that? Well, we talked about that at the beginning, that we want to have a probabilistic model of languages. So now you have probability distributions. So how does this create a probabilistic model for languages? The way it will create is that you have a string of the language and you apply the transformer. It creates these probability distributions for every position. If you had strings of length n, for the last position, it also creates a probability distribution. And then you would just sample from that probability distribution. So the probability kernel that it encodes, that maps all past strings to a distribution, is the probability distribution that you get at the last position of the transformer map. All of these are kind of thrown away. Like they're not needed. Okay? Yeah.
Isn't that unembedding layer mapping into Rn instead of to the alphabet?
It maps over a distribution over the alphabet.
Okay.
Yeah. And that's what we want. For every strings of every string length, we wanted to have a map from all strings of that length to probability distributions. Because then we can just do this generation of like one character by one character and then just keep going.
How big is D usually?
Big is the
How
key.
big is the dimension? D?
Capital N? This one? This?
Yeah,
D.
the workspace dimensionality of the workspace.
For small models, it's 256, 512. Bigger models, thousands. Big. And we should learn about the Johnson linear stress lemma at one point, which would tell us that that dimension is so big that you can squeeze a lot of information in it if you are considering this inner product geometry of like two vectors are, like there are many nearly orthogonal vectors in a 1,000-dimensional space. Hugely, like you should imagine it's exponentially big. That many nearly orthogonal vectors you can squeeze in there. And this near orthogonality, it's like you have all these inner products everywhere in the calculations. I mean, I didn't tell you, but like this just multiplies with a vector, with a matrix, and maybe takes a value and adds another vector. But this is going to be an inner product and an exponential, like lots of inner products everywhere. So this, that's why near orthogonality does matter, like how many different things you can do. Okay. So two things about this. So first, a generation. You can imagine what it takes to compute this probability distribution, right? So when you need to compute this probability distribution, you have to do pretty much all the work to compute everything else, but you will only read out this. But then, maybe something that's not so bad happens when you are in the next time step, and you generated something, and you want to continue the generation until stop is generated, right? Then maybe you can recycle a bunch of things. So you would cache a lot of things, but you cannot actually cache a lot of things, unfortunately. So as soon as you do this so if you didn't do the normalization, life would be beautiful, because you could just save the attention pattern. It's an n-squared matrix, and you would just like append one row and one column to it and be happy. But if you're doing the normalization, well, you can save the unnormalized matrix, and maybe that saves you some time. But you still have to do the normalization, and you have to recalculate things. And if you want to be true to the normalization, this normalization also changes how much you attended. If you, like the last position starts to receive attention, any attention, the other position attention is squeezed. So now you have to recalculate everything. Once you have to recalculate everything there, everything is gone. Like you can't cache. So it's like there is very little opportunity for caching because of normalization. So it's like it's brute force, n squared. So what do people do? Well, n squared is bad. Like you are generating tens of thousands of tokens, and you have accelerators and everything, but it is still bad. So people play around with this, right? So if in this sum, somehow magically, we didn't have linear in n number of positions to attend to, you would be fine. So what do? Like you're at a position I, and you already decided you only attend to the past because, well, the future is not being generated in generation mode, so that would be pretty ludicrous. So you're attending to the past, but maybe you don't want to attend to, like, it's like 1 million tokens have been generated. So somewhere 500,000 positions ago, like there is something there, but like, I don't care. Like I attend to the last 10,000 and then maybe the first 10,000 because maybe the user was writing the instructions in the first 10,000 tokens. And then probably relevant things are happening in the last 10,000 tokens, so you can do things like this. Or you can also do things like you're sparsely attending to some random positions, and like, so people play around with this, and almost all the state-of-the-art models are not going to do the linear calculation, but they will do some kind of speeded up calculation where they're sparsely attending to previous positions. People also, like it's an active area of research, mostly empirical research of what you should be attending to and what attention patterns you should use and how is this best done. It's kind of interesting. All right, so that's another Bayesian research, sparse attention patterns. Sparse attention. Okay. The next thing that we haven't discussed is that this thing, well, the whole architecture, this whole map is invariant to if I shuffle the order of inputs. Let's say you're summing up to it. Some people don't like that. Well, not when you're producing sentences, word order tends to matter. the meaning of sentences do change if you change the order of the words. So that makes little sense. So somehow you want to break this symmetry of the map. So this is an unwanted symmetry. Already, if you are only summing up to I minus 1, some symmetry is gone, but like still, too many symmetries exist. So people do various things. So one of the first things that people did was what's called positional embeddings. So these positional embeddings what happens is that the information before you start to do this query key calculation, somehow you want to encode the position indices. So you change the input to QL and KL. And the way you change the input is that you had X and you are at position I, then you add a vector that's specific to that position. So you create a bunch of vectors, workspace elements, and then replace QL XI with QL XI plus PI. So for each position, so here, these workspace elements are indexed by positions. And okay, so now we are kind of leaving the nice territory of a uniform architecture, where for every length, you do the same calculation. These are specific to lengths. And if you want this to work for any length, then you have to have infinitely many of these things. So that's a little bit problematic, but people nevertheless immediately did this. And same thing with the key calculation is also replaced. So in general, you can just imagine that the query and the key, before you do that calculation, you just add the position index vector.
So basically, this is part of EN, right? The encoding function, that time itself?
No, because it happens at every layer.
Okay.
And EN only happens at the very beginning. Yeah. Yeah, good question. This happens every layer, yes.
I guess in that, like, some architectures add it just to the beginning, and some add it at all the layers,
Yeah.
depending on what.
Right. Pass and whistles. Yeah, actually, you break the symmetry if you only do it at the beginning. Yeah. Okay, but people don't use this anymore. Here, this first the PI vectors. There was some suggestion that there should be some special vectors that some would represent positions. And then people were like, oh, but like we can train these things. So the advantage of training is that like maybe it will make more sense what you get. You have more flexibility, and your initial idea may not have worked that well, that great. And the disadvantage of training is that you can only train it for so many ends, right? Like, how do you generalize for lengths beyond what you trained for? That will not work. And the transformer architecture itself didn't have this problem. So now you introduce this problem. But, okay. People kind of still will deal with it because, as discussed previously, this is a beautiful, somewhat theoretical construct, but in practice, you take a finite context length window anyway. So. Yeah.
So AL takes the binary values. Does it cause problem in training?
No, AL in training will not do that. it will, so the AL business, it will use the normalized, and these are going to be vectors, and then you do the softmax transform. It's like exponentiate the gain of the inner products and normalize. So that could still cause problems, and particular scaling of like how these vectors are scaled so that the inner products are maintained, like n is getting bigger, for example. If n is getting bigger, can you still have, like you train some fixed, maybe, so in AL there is not going to be anything trained. In QL and KL you were training something, and can you create arbitrary sharp distributions that focus on, you know, like one token or whatnot, regardless of n, if you fix anything else? Well, the answer is no, that will not work. So what happens that if n gets large, then attention becomes diffuse and the models have a hard time focusing. So all kind of problems. So scaling is an issue. People, I think, fix that these days by, for every n, you try to pre-scale things so that the models work better for regardless of how big n is. So you can still get some sharpness. That just means that you have to scale manually as a function of n, the inner products, before you're applying the exponential function in the softmax transform.
Wait, what do they scale, sorry? How does that work?
So what happens is that, like, if you have many small values, then of course, like, large and small values overwhelm a big value. So you wanted to attend to this position with this big value, but you add a lot of chunk. And to save that, you have to scale up with the length of the chunk, basically. And then you are still sharp.
So that all the other places that have low
That's
dot
squashed.
products don't become zeros? Because
But they become essentially zeros, right? Like you want them to be zeros. Like you had a big value that for short sequences, it was totally dominating.
Yeah.
And then now you start to add a bunch of chunk near zero values in the softmax. Then if the number of those goes to infinity, they overwhelm this one value because this is a finite value. And so everything becomes uniform. So that's not good. So what you have to do is that you scale up is the number of elements that you have, that you're processing. Yeah. And then that could have some other limitations, I think, but this is, I think, state of the art. So there's that. Okay, what am I missing? Okay, so there are, okay. So in this picture, like it's impossible to draw it because it's like there is this matrix, right? So sometimes people draw this, like you calculate keys and queries and values, and then you kind of fill out this attention pattern of like I'm attending here, and then you collect the corresponding values, and then this value goes here, and this other value goes there. So it's like kind of pictorially showing you what happens. Where the important thing is that these are just the same network applied to produce all elements for above the columns and next to the rows, like these workspace elements and the values. So those are produced, and that's just linear operation, but then you have to fill out this matrix.
What does the function V do? What
The
is-
V?
Yeah, what is?
It's like, what's my contribution? Like like that's a value that I'm contributing. That's the intuition behind it. So the key and the query are like, I'm looking for this information. This guy says, I have the information. What is the information? This is the information. It's not the key,
It
but this is the
maps-
information.
It maps to the workspace, right?
Yeah, everything. Yeah. So you keep pushing everything into the workspace. Okay. Simplifying again, in most of the architectures, the workspace for key query value computation is tiny compared to the other workspaces. Sometimes workspace gets larger, and smaller. Oh, actually, okay, so for the value it's not true because it has to be the same as this. Question?
Yeah, so after the inner product, is there some weighting done as well to how much you would add to the value, or it's just like a boolean?
So the actual weighting is like this, which is a number between 0 and 1, right? Because it's like, you calculate this, like, you can think about it, you calculated this matrix, but then you normalize the rows, so that they are a probability distribution. That's the actual calculation that people do. And there they are exponentiating, so this AL, XY, is just exponentiating the inner product. So again, it's a softmax transform. And it's a fixed function, not log. Okay. All right, people are not happy with this either. So you have what's called multi-headed attention. So the way, I don't know, like people draw these things, but I don't know whether the drawings do make sense. But you can imagine that, okay, the flow of information is that you're doing this attention thing, and then the result is something, and then you keep processing it, you add an MLP, blah, blah, blah. You can do many parallel attention things. So you do a second one, you do a third one, so that from the same input sequence. And the reason for that is because you might have very many different types of questions that you might want to ask and collect information in different ways from other parts of the sequence. So these happen in parallel. It's called the multi-headed attention. And after you have done that, then maybe you're just like pulling everything together to one MLP layer, and then that's the next step. This pulling together is often done just like sum all the vectors that come out, and then let that be the input to the MLP. Because they don't want things to be too big. The vector space should be able to deal with this, like we're just collecting information here, like summing up. Ideally it doesn't destroy anything, it just adds information. Okay, so this is multi-headed attention. Oh, and then there is layer norm. So this is just randomly thrown in after every MLP layer or once in a while. I don't know when exactly. So you have all these vectors that you calculated for all the positions, and you just want to normalize it so that the empirical mean after normalization is 0. Sometimes that's optional, like sometimes they don't do that. And the covariance is what is the covariance? Want to do too much. I forgot. Like, I would be inclined to say that the covariance is square root D times identity. That's how I remember. Yeah, so I think that that's what they do. Yeah, indeed, yeah, indeed. So they do this little calculation So that's called layer norm. What's the purpose of that? At initialization, when you're initializing, that's kind of the statistics that you would see, the way people initialize things. And that was figured out to help with training in MLPs. And so people just think that generally, if these basic statistics, these first two moments, are off, we better normalize. So they just stuck in this layer norm into the architecture. Yeah.
Could you repeat the last part of the layer now? Like, how is the covariance?
The covariance after normalization should be square root d times identity.
Covariance of what?
The covariance, like you have n vectors that you calculated, and you treat this as your sample. And so the sample covariance after the linear transformation should be square root d identity. So it's basically doing a PCA.
Are all those MLP layers like dense things?
The MLP layers are, you have to, okay, so it's important, where is the MLP? So even though I drew it like it's a wide thing, it's the same as with this thing. It's components, it's applied component wise. So it's a tiny MLP applied component wise. So it's like very regular. So it's, when you're thinking about what this transformer is doing, like it's kind of doing this position by position calculation, and then when it comes to calculating the attention business, then it kind of like looks around and tries to collect information elsewhere, and then it does this position by position enrich the information that I already have. So you can think about the NLP is doing some association, right? Like if I already have this, and like what would I think is relevant? And like the NLP kind of like enriches it, adds something to it that is just from memory. It's like what I'm associating to. And then the attention is like, oh, like know that this occurred to me, like what else is relevant? That's kind of what it's doing. There's a story I'm telling myself. Yeah. Yeah.
Why do you want F to output a string of the same length?
We don't. It would be enough if it did this. It's a byproduct of this uniform architecture.
Didn't you just define F to output a string of the same length?
Yeah.
But you don't need it.
No. Just the last position. Normally, I mean, so some people actually, so origin of transformers, they were thinking about translation. Those are like, these are decoder only transformers. There's encoder, decoder transformers, BERT, whatnot. They try to solve translation tasks. So in translation tasks, the intuitive thinking is that there's a source language sentence. I want to encode the information about it in some abstract way. That's a string-to-string processing. Like if my sentence was length n, you kind of like produce length n thing, except that as well, you tend to look at just like last position again. And then you start to produce your output sequence from that. There is some story there, but it's kind of, it's a byproduct that you want to do this homogeneous way of processing things.
Do your embedding still component-wise, you would output a token, but then you just use the last token, or use the distribution of the last token?
You use the okay, so let's talk about that boundary. So when people are generating, you produce a distribution. By the way, why are we producing a distribution? Because it's more convenient for training. And the training is just supervised learning in the simplest case. You have your very long text, 100,000 characters. It's an excerpt, it's a program or whatnot, and then you shift it by one. So here comes an plus one, and you produce this pi n, and then you're like, oh, this is just multi-class classification. I should have produced an plus one. I produced this distribution. I have a loss, cross entropy loss. Let's minimize that. Train the weights of the networks involved, embedding, unembedding, the individual MLPs, query network, key network. A lot of sharing, weight sharing is happening. So that's kind of the strengths of the architecture, by the way. And so that's why we like this uniform thing that like, kind of like, it's very regular. You can feel that like, yeah, that should have some power, that you're sharing a lot of weights. Like if the structure is done right, then you should be pretty efficient to be trained. You should be able to pick up knowledge. So you do this training. And okay, so you do the training generation. You have the distribution. So one thinking is that, oh, I'll just like sample from the distribution. And yeah, a lot of times that's what happens. Sometimes people tweak it. So they would say, yeah, let's take the 5 most prominent tokens and let's discard everything else, and I just generate from those. There is also the max decoding, which takes the maximum probability token and returns that. Marcus Hutter, in my group, likes to say that, well, if you do that, then be ready that your LLM eventually will start to say and will not say anything else. Because once it starts saying that, how would it stop? So if it ever happens to that, so this max decoding is like kind of double-edged sword. The thinking would be that, okay, like that generates something more likely, but it is actually weird. It might degenerate to this. And then people talk about other ways of decoding because, for example, if you knew that, well, if you wanted to have the most likely sequence to be outputted, that would not be generated necessarily by randomly choosing one or just by this max decoding, because the max decoding doesn't care about that. Well, maybe now I should choose a lower probability symbol so that later there will be some really big probability symbol, so the total likelihood will be large. Okay, but with the total likelihood, the other problem is that but length matters. So maybe I can keep increasing my log likelihood is the right measure. My log likelihood if I keep adding to the length. So then there are some search-based procedures that are doing these funky decodings, beam search, whatnot. I think that mostly people give up on this. And these days they just run on the sample.
A few things. The one about not like planning for the future. So isn't that encoded in the data though? Like the data is such that like the probability that you probably learn to generate the next thing already has the knowledge that like, you know.
Yeah, so why do you care about generating a maximum likelihood sequence? I don't know. People so that it will improve results and reasoning tasks, which at one point we should talk about in this class. What are these reasoning tasks? Yeah.
Okay, and about the thing, like wait, when you append the word the to your previous sequence,
Yeah.
and you do max decoding, why would you output the again?
Well, because it's
Like why? Like it surely didn't learn that the comes after the.
why did it learn? I don't know. Maybe not do it.
The reason I ask is because in a lot of the theoretical things, they do use max decoding to simplify it.
Yeah.
I was thinking that, like, you know, you have this problem that if there is some word that is like unique in the language, like in English, then it's quite possible that like that happens with high probability, and like it just so happens that there are 500 other high probability things that could follow, but like the has like, higher.
Yeah, so I think that here the the on its own is not very likely, but if you have seen a lot of those, because it's looking for patterns, then it will be thinking that, well, if I have seen 10 those after each other, then this text is just about the. And it will start to say the.
But like,
It does.
it wouldn't see that in
kind
the
of-
training data, right?
No, it doesn't have to, because
Oh,
it
you're
learns
saying-
for patterns. It looks for patterns, right? Like repetition, like if it sees repeated stuff, it will
I see.
think that you should repeat
Oh,
stuff.
Yeah, but I guess that's an unlucky case where like maybe it generates a the after a the,
Yeah,
and then in context it'd be
Yeah.
like, oh, there's two the's, now I see the
yeah.
pattern.
So here we are kind of implicitly saying that we're thinking of this as a generative model taking a prefix and then generating an extra sequence.
Yeah.
But like the original task was to like encode the distribution over all sentences, right?
Okay.
So in principle, like, and that is like a multimodal distribution, right? Like in some sense.
I don't know what's the meaning of a mode here, but
Yeah, but in some sense the distribution is important, right? It's not
Sure.
just like so.
generation.
Yeah, in principle, you want to be able to start from an empty string and generate a representative
Sure.
sentence
Yeah.
coming from your corpus.
You can do.
Yeah, but you can't do that if you have like a max. thing,
Oh, yeah,
right? So
that's
you,
right.
you need to maintain distributions.
Right,
Not
yeah.
just like one.
Yeah, exactly. Yeah. Yeah, so, okay, so to defend a little bit the maximum decoding, if you have okay, let's say you have a math problem, but the answer is a multi-digit number, and you're producing the answer token by token, digit by digit. Then maybe, like 3-digit numbers, the maximum likelihood solution for the 3-digit numbers suddenly makes much more sense to look for than to sample, because you can correct some mistakes. So there are cases where maximum decoding seems to be sensible. Yeah.
Is it possible where you could just do both? In like some cases you do the maximum decoding, the other cases you just do.
Yeah, I don't like these hacks. I think that these is just hacks, and like, yeah, they should go away. But sure, like you can try. Just not excited.
But
Yeah.
if you decode one symbol at a time and choose one step maximum score, you wouldn't get a maximum likelihood
That's right.
sentence.
That's what I'm saying.
Pretty far
Greedy
away.
decoding is not good
Yeah.
for maximum likelihood decoding. Yeah. Okay. All right, so that's, yeah.
Okay, this is a little unrelated,
Yeah.
but I was a little confused about the difference between the decoder only and encoder only.
Okay.
So is it just about whether we're generating the next character versus looking for one in the middle?
They're also training them differently, and I'm not that too familiar with it, but these encoder-decoder networks, somehow, like there is some processing from the source language. It goes through the same steps. There is no unembedding. There is an internal representation. And then you already generated a prefix of a sentence. So you do the kind of the transformer computation, and at one point they just merge. And then after that, you just do the decoding thing. So that's how it is, right? So the source is like you could think about that's prefix to the prompt, but it goes through a different transformer thing, and it's mapped to some internal representation. And I think my understanding is that is why you just take whatever in the last position, the information you got, and then you use that at one point in the calculation, so that there's the other calculation that tries to predict the distribution for the next token to be produced for the translated sentence. So there are the previous ones, you keep doing the processing. At one point, this guy just merges and then throws its in information. And then from that point on, further calculations are happening, and at the end you produce a distribution. That's how it is. Yeah.
I think also, at least in the theory stuff that I've read, a lot of the time, like if it's just encoder only and versus decoder only, it just means whether they're using causal or cross attention.
That's a different thing. That's a misnomer. That's not how it is. Yeah. That's not right terminology, I think.
Really?
Yeah. This is causal attention or not causal attention. Oh, okay. So I know the reason. It's correlated. So the causal and causal attention is correlated whether you're using a decoder-only architecture or not. Because people, for practical reasons, for decoder-only attention, or decoder-only models, transformer models, they eliminated acausal attention because it's too slow to train.
Mm-hmm.
Since for translation you're slow anyways, you don't care.
Mm-hmm.
Yeah. And so there is a correlation there, and that's why maybe in the theory papers it's kind of identified as if that was necessarily the case, but it shouldn't necessarily be the case, but that's the case in practice.
Mm-hmm.
Okay. All right. Yeah.
So I have one question, like with this mathematical representation, with this like attention calculation, so we are quadratically like dependent on the number of tokens as well as the workspace dimension. Like it's n square and d square. Like does d square matter?
There is no d squared here.
Like if we assume that q, k, and b are MLBs or linear.
Hey, you take the inner product, that's OD.
Like if we are putting in multiple tokens, like
So here. This is n by n. You calculate q's. This is n times d calculation. You calculate keys. This is n times d. Calculate v's, n times d.
but like
After you have done this, you fill out the matrix entries. These are d-dimensional vectors here, like written for every column and every row. And for every column and row, you just take the inner product of the corresponding vectors. So that's n squared d, no d squared.
so initially we had x, which could be n by d.
No, x is okay. So at every position you have d, so altogether it's n by d, the dimension of the data, okay?
And then suppose q was some d by d layer.
Okay.
And like we assuming that.
All right,
it's
so that,
linear,
okay, so that is a d squared over there.
like, does that matter?
No.
Normally workspace dimension is.
I mean, like, you're on a GPU, TPU, so it's like that d is so small, you don't care. Like that, just like. So that's the job of the accelerator. It would matter on a CPU. You're right.
So we either have n times d squared or n squared times d, but we never have n squared d squared, right? And so that's why.
No, I think that the n squared is unavoidable with this.
Yeah. So, and because n squared dominates d squared, that's why we don't care.
Yeah.
about it.
Also, yeah. Yeah. Oh, yeah. Right. Okay. I don't know if there's any other person we saw.
Precision?
Right. Okay, what I will say about precision is different than what Vlad. So people almost exclusively do this on accelerators, GPUs, TPUs. Those are wonderful machines, but they are not known for their numerical accuracy. The developers gave up on implementing IEEE floating point, and that made it possible to scale to much larger sizes. The result is that there's a lot of numerical noise in these calculations. You should think about that. It's a very crappy floating point implementation. You don't have a lot of bits to represent the numbers. And does that bite you in practice? Well, I guess when n gets large, d gets large, then there could be something that becomes inconvenient, but I think that like the softmax issue, that you don't have sharp distributions, bites you first before you have any problem with the numerical issues. Yeah, theoretically, we'll see that, well, assuming infinite precision would allow you to do a lot of crazy things that are clearly not practical and not feasible. And so there you have to be super careful of what you allow yourself to think that you can do computationally. If you get into real numbers, a single real number has uncountably, that is too much, countably infinitely many digits. That encodes a lot of information. So you can put into a single real number a lot of information. And if you have nonlinear architectures like this, you could potentially extract that information, and you can put the worst knowledge into a single number. So that's wonderful, right? Like just one float, but with infinite precision. Yeah. So there you have to be careful. Right, there is, oh, I missed something. There is mixture of experts. All right, so once you discover that you can do this with the attention, you quickly discover, well, I can do something similar with MLPs. But you are not doing exactly the same thing, because it's like, if you would just have multiple parallel MLPs, that would be just like maybe one bigger MLP, like what's the point? So people do this mixture of experts variation. Where, so the MLP would calculate on an X input something. So you will have a bunch of these models, and you calculate a weight, which is also done with an MLP. And you have K of these, and you're mixing the output of them. And this is MLP. This is an MLP. But sometimes you do funky things that during training, you don't really use this MLP. You will try to train it to behave well so that it balances the load between the different MLPs. So the meaning of that is that across the many tokens that the MLPs process, on the average, each of the, so if you have tokens x1 to x, I don't know, capital T, that these are processed, and what you want is that across all of these tokens, for every I, this should on the average be the same across the different i's, which means that this should be T over K. Because then the load is balanced. And so during training, then you solve the matching process, where you're processing a lot of tokens, and for some, like these tokens, you're trying to calculate these matching weights in such a way that somehow the MLPs are voting that, I want this token, and you, given the votes, you calculate how many tokens you are routing to each of them, and then you also train the routing MLP to mimic this matching process. Complicated stuff.
This I thought it was supposed to be like a binary gate or something, no?
Well, eventually it could be a binary gate.
Oh, like what's the point of it otherwise? I thought it was just to like save on computation
No,
at test time.
no. It's like somehow
Oh, or yeah.
knowledge, I don't know, like specialization, I don't know, their stories. It's not saving on computation.
Well, I thought the story is something like, you know, if you have a neural network of size whatever, now you can have like a 10 times bigger one, but you only route it to like 1/10 of the. And so the computation's like the same as the
Yeah.
original one, but now you only route it to like, so it has like 10 times more knowledge, but it's only passes through a 10th of the network or something.
I think you're right that people also use this by choosing here the argmax and just routing to that.
Maybe, I don't know.
So no, that's what happens. But okay, so that's pretty ugly. But you still train this MLP, and then there is these votes, and you only use one of them. And the story is indeed that somehow it's somehow these are experts that are specializing in different things, and they're sharing the load, and so somehow a richer representation. But it's somehow sparse. Like it's not as complicated as adding another layer or something.
Well, if the idea is to balance things, why not just take the average?
Hmm?
If the idea is just to balance things, right?
No, but then they would do the same thing, or like there would be no advantage to using a mixture. You want them to specialize. You're thinking about that, well, this network has to solve many complementary tasks that live in peace. Each of them requires some simple processing. Together, they require complex processing. But it's not too complex. It's more like, I look at this input vector lies in this subspace, then this is how I should process it. If it lies in that subspace, this is how I should process it. That's kind of the thinking.
So for different vector, you want to activate different.
Yeah, different routes. Okay. All right. So in practice, you fix the context window length. Oh, I didn't do the rope. Okay. Somehow we started to talk about these position embeddings, and there is a lot more to say about that. But maybe I just tell you what people mostly do these days. So instead of doing this, what they do is that you have a position-dependent matrix acting on the queries and on the keys. So the actual query value is going to be the query network applied to X of I, but then you rotate it with a rotation matrix. And same is the keys. These are keys. So for the ice position, you apply a position-specific rotation.
Do you learn this or you specify?
I think that you specify it. And it's going to be something that is kind of funky. Like the dimensions are going to start to have specific meanings. Like dimensions with low indices represent rotations no index. That rotations that are tiny and positions with high index represent rotations that are big. And you do this, I don't know, like you're pairing up the dimensions, like, because you use sine, cosine, blah, 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 so that the math kind of works out nice. And when you take the inner product of these two guys, then what happens is that you're effectively going to be sensitive to, well, I shouldn't. So there's QL, XI, transpose, and R. So these guys, the way they work is that if you multiply, I think, okay, so there is a transpose going on because you're gonna transpose this. So when you transpose that, that's rotation with degree minus I, and so this thing is just this twisted inner product where you have a rotation that's effectively depends on how far away the two positions are from each other. So this I minus J difference, like that's how big the rotation is going to be. And so the effect of that is that if the key and the query networks, sorry, this is QL, do not know about this rotation business. They know about in the dimensions, the rotations are going to happen, like in the different components of the vector, different amounts of rotations are going to happen. So they can prepare to that, but apart from that, they don't actually have information about what is I and what is J. So they just do some processing, and after that, they look for a match. We are looking for a match. But we are going to rotate off the vectors if they are further away. And if the vectors were originally matched, then you're rotating them off, then they are less matched. And somehow this depends, obviously, some dependence on how far the positions were from each other. And then you tell the network during training, use this information to your advantage. And the thinking is that, well, it's the relative positions that, position differences that matter most, not the absolute position differences. So this is what people use these days.
So since we want this kind of thing where we care about a relative position,
Yeah.
why do we need to do all this stuff with the matrices? Why can't we just define AL to be a function of I and J? Like that doesn't change the computation cost or anything, right?
It is effectively doing that, right?
But we don't have to encode it as, like we could just directly have said that AL is some different inner product based on
It
what
is.
I- yeah, okay.
Effectively, this is what it does, right? Like this calculation, so that you're doing this, that means that AL is IJ dependent.
And more generally, since we only ever care about the composition of AL, Q, and K, like why do we
Yeah.
learn all these three for the Q function, the key function, and the A
Yeah.
function? Why do we learn all these three things separately?
Oh, AL is not learned.
Yeah, just the inner product.
Yeah.
But like, why can't we just say that there is some generic function of xi and xj that gives you a number?
I think that you want the uniformity and you want to enforce this, that like these networks should not that much know about the positions, and I don't know, like, I mean, instead of, okay, so why the inner product, why the softmax, I don't know, like it's historical reasons, like This is what people thought about, and like, why not learn the whole thing? I don't know, like, you could try. I bet people try certain things, but yeah.
I don't know if it's a well-defined question, but I mean, we have a lot of elements, we have a lot of freedom. I mean, can't we just, for example, instead of this rotational stuff, play with V or other things and do the same thing?
No,
No?
no. Because those are invariant too. So the I, J indices do not appear anywhere. So it's kind of too late, right? Yeah.
Is it more so about the magnitude of the rotations as they relate to how far the positional embeddings are?
Yeah, I minus J. Distance between the positions. That's the amount of rotation that these guys are gonna see. Right?
I was talking about like more so like, I don't remember how rotations are done in higher dimensions, but this is not so, it's just about the rotational magnitude, but more so.
By the way, they are doing two. Okay, so this is what I do. There's no high dimensions here. So you have a d-dimensional vector, and then you chop it up into d over two two-dimensional vectors. And now you're thinking about the two-dimensional vectors and the inner product between them. And for every two-dimensional vector, you apply a different amount of notation. There is a scaling factor here of like that at the first component, the rotation angles are tiny. Second component, they're twice as big. Third component, 4 times as big, and so on and so forth. This is what they do. Yeah, so they know high dimensional rotation. It's kind of like this sequences of two-dimensional things. And then it's the job of the neural network to figure out that this is the human designer doing. It's like, yeah. It's interesting, but weird. Okay, I think we should stop here. Thank you so much. See you on Thursday.